Okay, in this chapter 12, I just want to introduce this new geometry. I think you already saw this one before a lot. Okay? But the amazing thing about this fractal geometry is it starts like last century, right? Like 20th centuries, in the middle of it, like 1970 or something like this. It's quite young mathematic area, right? It's only 40 or 50 years old one. And it's really developing right now a lot. Even some definitions are not fixed yet. People are arguing about that. Okay, so like what is the definition of chaos or something like that. But it's not the same area, but it's very similar in that area. So I just want to introduce what really the main things in the developing these fractal geometries. Okay, and I wanted to share with you some softwares so you could play with it. Okay, so we offer another course about the fractal geometry. So if you're really interested about it, please take that course. Okay. So please, it's just reading subject, right? So please read by yourself, right? I don't need to read for you, right? So please just read this one. But one of the main thing about this is, as you can see here in your PDF file, you can see those animations, right? Now, listen carefully. I already mentioned this one before, but uh, when you click your study book, it opens within your web browser, I think, right? Then within the web browser, you cannot see this animation, right? You have to download this PDF file into your computer and open it with like Acrobat, Adobe Acrobat Reader or something like that, right? Then you can see these animations. So if you want to see again, click that. It returns back to the original position. So that's a famous Pensky triangle. And for animation, just click this play button, triangle shape. Then actually it's zooming in into one of the part of this entire shape. And when you kind of magnify it, it's nothing different, right? The original ones and this one quite looks same, right? And it's actually same, right? So that's the power of these fractals. Especially one of the characterization of fractal shape is a self-similarity, which means if we ignore the scale, then a part of fractal shape is exactly same as the original entire shape. That's one of the biggest characterization of fractal shapes, right? So this is really nice example about it. And good thing about this type of fractal geometry is uh, the one of the kind of the researcher in this area actually has some idea about that, using this fractal to save the image. You know, if you try to save some image as it is, then it requires a lot of space, right? And if you just compare any Word file and just a small picture file, then you know how big that picture file should be, right? So just imagine you kind of try to save this one into your data. Okay? Let's say you make an encyclopedia, okay? And it requires a lot of pictures on it. So text is just nothing. The entire text is just nothing, but the pictures really requires a big space over there. So the idea is no matter what pictures you take, when you look at it, some portions looks very similar to each other. Okay? No big differences. Even you compare this area and that area still. And even within there, if you magnify those, then this area and that area might looks like very same, right? Then if we have some rules about transforming and translation, then if we have some information about that small area might be translated to some other area which has very similar pictures and textures like that, right? Then all we need is just how to send that small pixel, let's say, into which area as a function. And all we need is what is the color and the texture and brightness, just that much information. Then instead of memorizing, look at here, if it's a 32-bit and 64 bits, then for each small pixel, we have really, really big data to save all the information, the color, texture, hue, and everything, right? And for this big picture, right? But if we apply this fractal style method, then we can reduce this big picture data into some small text data. So when people open this kind of, let's say, encyclopedia using computer or whatever, then the actual data doesn't have any picture in it. It has only the method how to reconstruct this entire picture whenever it's necessary using these functions and like that, right? So that was his idea. He was that much close to make a contract with Microsoft. Okay? And I heard kind of it's off, but that was his idea, and it's really brilliant. Okay, so so that's the one of the use of these fractals, but there are many use of that, and it's a kind of young area in math. So most of them are unknown yet. So if you do any research, if you are looking for some position or job in the research area, and if that research has done like the last several thousand years, then it's very difficult to catch up the known things, right? But if you go this type of new area, then nobody knows anything, right? So you just scratch up something, then it's a new thing, right? You did it and you find it or you made it and under your name, okay? And you are the expert suddenly, right, in that area like that. So if you're interested in math, then if you're interested in geometry and those type stuffs, right, you still need to using some fractals and uh, differential equations, everything in there, but right. So you are gonna go to the edge of this area, right, very soon. So please thinking about it. Okay. So please read what's going on and what is the Mandelbrot sets and like that. But let me just kind of run through. So briefly, right? So I'm not going to cover what the Mandelbrot and the Julia sets and like that, but I'm interested about this and self-similarity and L systems, right? So in this lecture, I only talk about that part, okay? But the other part, please read, is interesting. Okay? This is a famous Spassky cascade or triangle, and we already saw that how similar each other, right? And the scale, if you just ignore the scale, right? Okay, so that's the another kind of animation show how to get that specific triangle in different way. Okay? So in the previous case, we haven't done anything how to make it, right? One of the method is starting from this solid triangle and cut out the middle triangle, right? So let me step one more, right? Remove it. Then for the remaining three triangles, we just cut out the middle of each with the same ratio, right? As we did in the first place. So like that, right? Then we have 9 left over small triangles, right? Then we just cut out the middle of each these 9 small triangles in the same ratio, right? And just keep doing it and keep doing it. Then we are going to get that Spassky triangle. That okay. In this case, after we do that, we got the exact same kind of Spassky triangle. If you're zooming in into any area, right? Not only this big case, just go that much, right? And even smaller than there. Still, when you magnify it, you're gonna lose nothing, right? You just recover the entire ones. Okay? And this is just showing, right, how you just go into there, something like that. Okay? Now, next famous one is cut curve. Okay? This one is iteration of this cascade. Okay? And cut curve, we are going to see that one later, a bit here, so using L system. Okay? Now, the L system is developed someone, okay, says Lindermeyer, is around 1968. It's very close. He's actually a biologist, and he tried to kind of sketch these plants with very simpler way. Okay? And this is one. This is the cut curve, right? So the method is, for the given line segment, we just bend the middle third. Okay? So make it the length as same, right? Congruent each other. So just kind of push and make a dent like that. Then for the leftover line segment each, right? So we have 4. When we started, we have only 1, and make the middle parts like this way. Then in the next step, we have 4 line segments. Then we did the same way for each one of them, right? Can you see that? So push like that way. Then we have like a 16 line segments in this step. Then for each of the 16 line segments, we do that kind of denting for each one of them, right? Then we are going to get that. So if you just keep doing it, eventually at the end, we are going to have that shape, which is called curve. And when you magnify up any area, that one looks like this one exactly, right? So like that, I mentioned that someone really tried to make a contract with the Microsoft, right, to to save the picture using this kind of concept. The one good thing about, there are many good things about it, but the one really good thing about that one is, yes, save these the hard disk space, right? Another thing is, in the regular style of picture, when you magnify it, you are going to get just a dull picture, right? You cannot see the clear ones, right? But just imagine if that picture is produced by this style, then when you magnify, still you see crystal clear pictures. Okay? Theoretically, right? Of course, there are many things we have to take care of it, but okay, the main idea like that. Okay? So it's really, really much better than just regular style pictures only. Okay? So he just developed his own way. I'm going to explain that one a little bit later. And he did interesting about using this one to doing something else, but all the people really interesting about it, and they really kind of go into that way and producing this type of stuff, right? So this is what actually the person kind of has an idea. Very similar style one. Start with some line segment, and it gives some kind of order. In the previous case, like a chunk out the middle of the triangle or dent into the middle of a line segment, right? So same thing. How about given line segment, let's put 2, like a half size of line segment, okay, into certain angles. You can arrange that angle whenever you need it and keep doing it, right? So in this case, this one already has those 2 branches, right? So let's just apply those rules for that the tip of those 2 branches and keep doing it. Then after certain steps later, it looks like it's not that much like, oh, it's just only line segment, right? It's rather, looks like, yeah, nice kind of cauliflower, right, style outcomes. And in nature, we saw that style a lot, right? And this one also shows that kind of style, right? It's more changing the shapes and like that. So it's more looks natural, but it depends how you look at those, right? So anyway, these are the fractal tree we call, and it can be done by several different ways, and one of them is a system. The other ones, we need more time and more softwares like that, right? So at this moment, I just want to introduce one site which has that. Okay? So in this case, oh no, it's not here. Sorry, this one. It's in your study book, right? So you can get this site. So as you can see here, we can get the specific triangle, and it comes with all these ideas. So if you want to see something else, like this type of really looks like some tree, okay, or bushes. So when you click it, it changed the order, right? And it produced that. Can you see that? How close the actual picture of some bush, right? But when you make it the initial shape is just like this. Can you see that? So you see just iteration of the similar pictures into a smaller size in each places, then eventually you're going to get, after only 5 iterations of the applying same function, right? So that's the entire kind of concept. In the beginning, all we need is that simple kind of collection of few line segments, right? With the specific angles and like that, right? So only initial first iteration, it just looks like that, right? That's it, right? But apply this one 4 times more, like iterate up to 5 times, then suddenly that whole picture looks like much natural. Okay? How about the others? In this case, the first initial condition is like that. And as I mentioned before, the concept was, okay, how about just reserve this information only? And this is not a picture, it's just only data like that, right? Especially like those kind of functions, right? These are functions. So it's just text. And we have really fast, strong like computers everywhere. So whenever people open that encyclopedia, for example, open that page, then suddenly the computer just start working on it, iterate only 5 times, starting from this dull picture or some data, then suddenly we got much natural, okay, way of these bushes like that. Okay. So play with this one, and we are gonna have the homework assignment. Play with this one, right? So all you need is just after you do that, I'm just shooting down to show within that this video, right? But like make it bigger, okay, and show entire one. So all you need is just take a picture of this, including that result, right, together, and just include into that Word file and just send it to me, okay? I mean, submit that one. Okay, so in the else system, this is how it's gonna work. In the beginning, the command usual the command is alphabet, but recently it changed, like using 1, 2, 3 doesn't matter. So but most likely people start with F for one line segment. So the capital F means the vertical line segment, and we kind of ignore the scale, right? If it's growing up, then we just shrink down and see all the results at each step within the same window, right? So in the previous case, this picture shows in the same dimension, but when you study it, the initial portion only shows that much, right? And if it's a next step, if it's bigger like that, then we just shrink down that one and see within this window size, same window size. Okay, so please remember that. So uh, size at this moment doesn't matter, but angle is important. How much you're gonna change the angles like that, right? So when you study it, these are the kind of types of commands we need, or kind of operators. So capital F means vertical line segment, and small f, and it can be defined all different ways for all different softwares and literature, right? But most likely we need a dark solid line segment, or sometimes we don't want to sketch anything, we just draw it, okay? I mean, without drawing, we just want to go that much distance, right? Then it's small f here. Plus means like a rotating or turn counterclockwise that much, and minus means clockwise turning, okay, for the specific given angle. Okay, so that's the concept. But in that site, I couldn't find what is the command for that small f, like just go that much distance without drawing anything. I couldn't find it. So all your homework is just something without small f, okay? But please remember that there is something like that, okay? So this is how it works. For any typical L system, the Lindenmayer system, F is given axiom, which means what? Oh, start from one vertical line segment. That's it. And this is a function. So F goes to the image, it looks like this way. Then the meaning is start with F. So you go to the vertical line segment. And minus means take the clockwise turn. How much? Maybe 90 degrees, 180 degrees, 45 degrees, depending on what angles you have, right? But just rotate that much. Then go to that direction. So as you can imagine, like you just go to certain direction and take turns and go to the same, go to that direction into that much. And plus plus means make the counterclockwise turning twice and make the line segment and change back like that, right? Can you see that? So this is just the first iteration, right? Starting from F. And when you apply this function, this is image, then we got this one. But when you apply same formula to this result, so it's a second iteration, then suddenly each single f changed to this one, right? The original definition. So this 4f kind of string changed to this 16f string. Can you see that? So the first 4f, this much, should be copy of that, right? And it's just result or image of that first step. And we have minus, so minus goes to minus, minus is there. And the second f compared to the next group of these four f's. You follow me? Keep that like that. Okay. So you can imagine like a 5 iteration is actually what? Make it power 5, right? So 4 pieces, 4 goes to what? 4 to the 5. Okay, so we can imagine how many f's in that after 5 iterations of it, right? And you know, that's why we could get the picture very fast, right? And that is actually for the cocker, right? So let's say, let's just practice this one. I have my own one, much better one as a software, but let me just use this site, okay, because you need to go there. So you have to use this one. That's the only one you have. So it's like this. Before starting anything, one. And angle, cut curve is, I think it's 60, but let's see. The axiom is just F, one single line, and the F goes to that one, right? Oh, it doesn't understand the plus minus, so you have to type it in. So F minus F plus plus F minus F, okay? And that's the only single rule we have. And let me start. Okay. So first iteration, can you see that? Like this. And the reason it's tilted is because F means what? One vertical angle, right? So you can rotate it if your axiom is like that. But right now the angle is 60, not 90, so we are not going to get the nice horizontal ones, right? So if you have like this, then start, then you take what? The 60 degree rotation, right? So you know what I mean? Okay. Or if you start from plus, then it's a counterclockwise rotation, so you're going to get the other way. You follow me? Like that. So if you want to handle that, then you really want to see that horizontal way of stops, then there are two things must be satisfied, because this angle starting from 1, we need 60 degrees, right? So somehow we have to handle 60, but to change this vertical angle to the horizontal, vertical line to the horizontal line, then we have to rotate 90 degrees, right? So somehow we have to handle 60 and 90 degrees. Then I'm just going too much detail here, but change the angle to 30 and change this number of plus minus is twice, right? So like that. Hopefully it's working. Like that, right? So 1 minus change to 2 minuses and 2 pluses change to 4 pluses, and then we can start with plus plus. Okay, you see that? Ooh, successful. Okay. But let's change to 2 iterations. Can you see this? So if you just because my video size is small, so I cannot show you all together. But when you do that, okay, please check by yourself how it's changing, right? So let's change this one to up to 5. Then this is result, right? Okay. So all you need is how you're gonna give those function, right? Command, then you can construct those. And of course, there are slight kind of modification for each different softwares to handle L systems, right? And especially like we really need those small f, like a lot of times you have to go a certain place without sketching anything, right? So you cannot do this one unless we know how to get the small f. Okay? I typed it, small f is not working with that site. Okay? Even you can sketch those Hilbert space filling curve. And when I was in PhD program, actually I made this one by myself, and later it turns out Hilbert did already. Okay, so, and this one also shows how this kind of command is working, right? Starting from F. Okay, good. And the direction is that way, okay, for its own direction, because always direction is important when you're thinking about the rotation, right? So going up that much. The next step, okay, the bracket means you remember that place, and the close bracket means go back to that place, right? After you finish whatever. So plus means counterclockwise, maybe it's a 30 degrees, right? And sketch that string, right? Then the direction must be that way. The next one, again, to remember that place, right? Because it's another open bracket. And plus means another rotation and sketching. Now, you close it, which means after you finish this, go back to that place and do it, right? Can you see that? So this is how you sketch several stack or the line segments starting from the same point, right? Using this bracket. And close it, which means you have to go back to that place, right? So it's kind of a bookmark, right? And whenever you got this matching closed bracket, you go to that place and be ready, okay? And be careful about the position of bracket. We got rotation after bracket, so your place is here and the direction is still that way, upward, right? Because it didn't apply that plus yet, right? And you remember that place and doing something else. Now it's negative. So look at here. From that direction to upward, that plus makes counterclockwise maybe 30 degrees. But we do here on the same place and same kind of direction and take the clockwise rotation 30 degrees. So we are going to get this line segment and do the same thing like that. Okay, so this is how you read. Okay, how it's going to work, and small changes get whole different results at the end. Okay? Okay, so let me talk about this one first. Okay, the homework. So all homeworks are about L systems right now. Okay? And go click just that one, then it goes to that site. Then all you need is just use those axioms, right? And product rules. And right now, just use 90 degrees for the angle and 5 iterations for all. Do not keep too big number for iterations. As you can see here, if you change that on to only even 7, 8, 9, depending on the rules, it takes a lot of time. Sometimes it makes your computer frozen. Okay? Too much calculation, right? So be careful. That's much powerful. Okay, like that. So please just check, and after you got the results, every time just take a pictures. So put down this one in the Word file, and put your pictures of your result there, okay, and do it. And after you finish your homework, change those angles, right? What happens? And change small things like just removing one minus and removing one F or adding more, and see how big changes appears in there. Okay. Okay, so that's the homework, and I'm gonna cover the remaining ones in the next video.